welcome to this explainer. Okay, let's dive into this. Picture this. Right at this very moment, a billion-dollar spacecraft is just hurtling through the pitch-black void of deep space. And, if something goes wrong out there, say an unexpected asteroid, a sudden system failure, or maybe it needs a critical course correction, there is literally no human around to press a button and save it. It's kind of this harsh reality of deep space exploration that we rarely think about when we're down here safely on the ground.
And the stakes? They're incredibly high, all because of a simple issue of physics. We're talking about the communication delay. Imagine a spacecraft hits a sudden emergency. A distress signal, even traveling at the literal speed of light, takes 20 long minutes just to reach ground control. And then, assuming NASA engineers manage to instantly whip up a life-saving fix, it takes another 20 minutes for that command to travel all the way back. That is a 40-minute round trip where the spacecraft is essentially paralyzed, just waiting, helplessly, for instructions from over 140 million miles away. For 60 years, that agonizing wait has been the ultimate leash on our ability to really explore the universe.
Which brings us to our first major roadblock, Section 1, Trapped in Ancient Brains.
And this brilliantly illustrates the core problem. Because deep space radiation absolutely scrambles standard electronics, NASA has to rely on specially armored, radiation-hardened processors just to survive the trip. So think about this. While the smartphone sitting right there in your pocket can perform trillions of operations per second, a billion-dollar NASA spacecraft is essentially running on the equivalent of a bulky desktop computer from the early 2000s. Yeah, we are literally exploring the very edges of our solar system with the computational equivalent of a machine running Windows 98. They simply cannot process heavy data or make complex decisions fast enough on their own.
But thankfully, that era is officially over. Let's look at Section 2. The 500x power breakthrough. So NASA and microchip technology unveiled this really audacious goal: build a processor powerful enough to run modern AI, but physically tough enough for the harshest environments in deep space. They call it the High-Performance Space Flight Computing Project, or HPSC. Now, what's really interesting about this slide is recounting what happened in February 2026. Engineers inside a pristine clean room powered it on for the very first time. And, in a totally poetic nod to the first message ever sent over the internet, they used this brand new chip to send a single email. The subject line? Hello, Universe. It was just a quiet moment in a lab, sure, but the results of that initial power-up absolutely stopped those engineers in their tracks. Because this new chip, which, by the way, is remarkably small enough to fit squarely right in the palm of your hand, operates at nearly 500 times the performance of current space processors. 500 times! I mean, we aren't just talking about some incremental, year-over-year tech upgrade here. We are talking about a game-changing paradigm shift, one that completely rewrites the rules of what a deep space mission is actually capable of doing.
So, how exactly did they pull this off? Well, this technology is what engineers call a system on a chip. Instead of having separate, fragile components just spread out across a giant motherboard, it packs an entire computer. We're talking the processing units, the memory, the networking, and all the input-output pathways into a single, highly durable, radiation-hardened package. By centralizing the whole shebang into one tiny unit, they've basically created a computational brain that is incredibly efficient, deeply integrated, and heavily armored against the brutal conditions of deep space.
And that design brings 3 truly revolutionary features to the table. 1. It's fault-tolerant. That means if one part of the chip gets zapped and damaged by a stray cosmic ray, other parts instantly and automatically take over the workload. 2. It's flexible. If mission parameters change years after launch, Earth can reprogram this chip completely mid-flight. And 3. It's fast, like almost incomprehensibly quick by space computing standards. Basically, it's designed to survive, adapt, and thrive in the most violently unforgiving environment we know of, without missing a single beat.
Let's move to and see how this builds into something even bigger. Section 3, spacecraft that think independently.
Remember that communication delay we talked about earlier? The old method of cautious, delayed exploration meant a spacecraft had to wait up to 45 minutes for Earth's permission just to steer around a hazard. But with this new chip, the reality flips completely to analyze, decide, and act instantly. Picture a modern lander making its final approach to the surface of Mars. Instead of just blindly executing a pre-programmed landing sequence and crossing its mechanical fingers that the math is right, this new lander can analyze the terrain in real time. It can spot a hidden crater or a dangerous boulder and dynamically adjust its descent entirely on its own. No waiting for ground control, no agonizing delays, just instant action.
So the crucial point is that this chip doesn't just upgrade a spacecraft's hardware. It effectively gives the spacecraft an independent brain. Think about it. Mars rovers aren't going to just crawl a few feet and then wait a full day for mission controllers to approve their next move anymore. They'll be able to drive, explore, and navigate the Martian landscape totally independently. Probes orbiting Jupiter, they'll be able to spot a sudden mind-blowing scientific anomaly, like maybe a subsurface ocean geyser erupting, and instantly redirect their cameras to study it without waiting for a human to tell them to. And for future astronauts heading back to the moon or onward to Mars, onboard AI, powered by this chip, will instantly assist with life-or-death medical or navigation emergencies. You know, those critical moments when they simply cannot afford to wait for a doctor's advice from Earth.
Which brings us to our final act, Section 4, when machines decide alone.
Because for 60 years, the absolute golden rule of space exploration has been human control. A human designed the mission, a human programmed the commands, and a human pressed the button. But this chip, it officially breaks that 6-decade chain. And that raises a massive lingering question for us. What actually happens when machines decide alone? What happens when a highly autonomous probe deep in the cosmos encounters something completely unexpected, some strange anomaly we never even programmed it to recognize, and it makes a decision to act on it before Earth even knows it's there? It's kind of wild to think about. The very technology that makes these spacecraft vastly smarter also makes them radically independent. And out there in the dark void of space, that independence is absolutely our greatest tool, but it's also the ultimate wild card.
Right now, NASA is rigorously testing this chip. I mean, they're blasting it with radiation, freezing it with extreme cold, subjecting it to intense mechanical stress, basically doing everything they can to prepare it to fly on the next generation of missions. Which brings us to our final takeaway today. The universe is waiting, and so is the chip. Somewhere out there in that vast, pitch-black ocean between planets, a spacecraft is going to face a choice that no human could have ever anticipated, and it's going to decide, completely alone. What that machine decides, and the unimaginable secrets it might uncover just by thinking its own thoughts, well, that might just lead to the greatest discovery in the history of human exploration. Thanks so much for joining me on this explainer. I really hope this sparked your curiosity, and I'll see you in the next one.